Get yourself a calculator if you don't already have one. Learn how to use it. The things that give students the most trouble with calculators is, where's the log function? What do you do if you need to find the anti-log? You all had algebra where you've done logs and all that. Okay, so the anti-log is just for common logarithms. Definition of logs, and it's understood to be base 10. Log of x equals y. Okay, what that means is 10 to the y equals x, right? So this is the log of x. This would be the anti-log. If you know the log, you want to find what x is, then on your calculator, you take that value in as the power of x, and that gives you power of 10, and that gives you what x is. Okay, so on your calculator, you probably have a key that has log on it, and then as the function above that push the function key is probably 10 to the, it'll say 10 to the x, but in our case it'd be 10 to the y. Okay. Things like that, learn how to use those. If you forget your calculator, I keep one spare here. Okay, I never use it because I don't like algebraic calculus. My calculator is probably one you don't want to mess with. It's called RPN, which is reverse Polish notation. The advantage to this is, once you get comfortable with it, you don't need parentheses. You never have to use parentheses. It's just the way it's. You put in, you say, like 2 enter 2, and then what do you do with this one? Well, if I want to add them together, I press the plus key, and it gives me the answer is 4. Or if I want to subtract 2, I just push the minus key, and it gives me 0. There's no equal sign in an RPN calculator. I mean, but if you want to use one, I'll let you borrow it for a little bit. It's just, it takes some getting used to, but I mean, after you get used to it, it's just head and shoulders above algebraics. They just, algebraic calculators like Texas Instruments, they probably have a better marketing scheme. Well, back to the topics here. Learning outcomes, course outline, those are pretty much required. I put those in there. And there's a lot of stuff in back here that's also required. So I'm going to point out stuff that's unique to this course. So I'm sure you want to know how you're evaluated, right? So we will have regular exams, and that's on page 3. And then on the following page, page 4, I have a calendar. That tells you what we're doing when, and where are the exams, when's the homework due. For instance, today on the 20th, we're doing this class business, plus we're going to cover chapter 1. That's activity over there on the right. That math test, I left that in there. I should have taken it out because Cengage has a math test for you. It's not graded, but if you take it, it'll tell you where your weaknesses are. If you have it, if you feel comfortable with, if you did well in algebra, you'll do fine in here. That's no problem. So I'm dispensing with that math test. And then we'll have a review on the 27th. So we'll work out any kinks for chapters 1 through 3. And then the following Thursday, on the 29th of August, we'll have an exam on those 3 chapters. And the homework is due on the day we have the exam. Okay. Because if you haven't got it done by then, it's not going to do you any good anyway. The rule is you don't get credit for your homework if it's late. There's no late penalty. Well, there is a late penalty, it's 0. But like I said before, since this is new, I'm going to cut everybody some slack because I'm learning too, and we'll figure it out. Maybe by next semester, everything will be smoothed out, and then I can be hard-nosed for the next class. But unless something major happens, then this is the schedule and it's chiseled in stone. So you know what's coming and when it happens. I have built in some buffer days in there. You'll see quite a few. That's so if I get long-winded, we'll have some space, buffer space, so I can complete the topic. The general, here's the approach, educational approach. Introduce the subject. Reinforce. That includes homework, review days, things like that. And then assess. Those are exams. And homework is a form of assessment. So it's IRA, individual retirement account. Introduce, reinforce, assess. I like to keep it real simple. So there's homework. Let's see. I've explained that to you. The only two that are graded, mastery and EOCs. You get 11% credit for attendance. And like I said, I don't excuse absences for attendance grading purposes. You know, I recognize that, you know, you might have family trouble, snow days, if you have small children, you have to stay home, things like that. So one of the ways that we get around that is we use Zoom. Right? So in Blackboard, we call that over here. Here's the Zoom meeting connection. Right here. So you click on that, and it should show you your class. It might show you a whole bunch of classes, but yours, and it'll show you the one pending. And you just click join. If you have access to Blackboard, you click join, and you should have a webcam on your laptop or whatever, so I can see you and you can see me. And then a little inset here with your image will be there, and I can see that you're here, and I'll mark you present. Okay, so you can zoom in and be counted present if you can't make it physically. Now, there's an alternative. Let's see if I put that in. It must be in the Appendix 2. So we go to the back again. Appendix 2, here we go. So Appendix 2, Item 2 is the Blackboard version, the way to get into it through Blackboard. But if you don't have access to a computer, say you've only got your smartphone, and you want to zoom in, you got stuck somewhere. Maybe your car's getting fixed, and all you got your phone. Right? So while you're sitting there in the waiting room, you can, well, you'll have to have this number with you in red, that number. If you click on, if you enter into your browser in your smartphone, newriver.zoom.us/download, that one will allow you to download the Zoom app. Once you get the Zoom app in there, then all you have to do is click on the Zoom app or tap the Zoom app in your phone. And it'll come up and ask you for the meeting ID. And that meeting ID, 207-341-990, will connect you to the Zoom in progress. Okay. So you can come in on your phone if you want, if you have to. Not the ideal situation, but it's better than nothing. So maybe somewhere in your phone, mine has a little app called Notes. So I put information in there that I need to have access to. And you may want to put this course and the address and that ID in your phone somewhere. So if you have to come in on your phone, you got it there for you, and you can punch it in and you're in the show. Okay. Now, what do I do with these recorded videos? I record them so that they end up on the computer. We have an option. They can send it to the cloud, or you can put it here. I don't know where the cloud is, so I send it to the computer. Because if the cloud goes down, I've lost everything. So I have the file, the video file on the computer, and then I upload it to YouTube and put a link in Blackboard to today's activities. Okay, they should be fairly easy to find. I did this last semester for CHEM100. And when I copied the course over, all of those links came with it. So the links that you see now are to last semester's discussions. But as we get our own versions, then I'll put those in there also. Okay, so you can go back and review what's happened in class. Like I said before, if you miss 50% like most students do, then you can pick up the other 50% by looking at the videos. Okay. Let's see, what's next? So that constitutes your grade, 69% for exams, 20% for homework. One of the reasons I put homework in here, well, actually two reasons. One is I was interested in, what do they call it? Active learning. The system that in general, active learning is a system where you can, you do a problem or answer a question, and then if you get it wrong, the system responds with a hint or saying, this is what you did wrong, this is how it's wrong, try again. So that's active learning. And it seems to work fairly well, so I thought I'd try it. Plus, since you get 20% for your homework, it's a less stressful environment. I know some students have test-taking anxiety. Some of them are really severe. So this is an opportunity to make 20% of your grade without the stress of an exam situation. I couldn't do away with exams altogether. Tradition. Okay, so there's your schedule. Let's see. This other stuff is a lot of it's common sense. So I'm going to let you dig through that. Exams. If you miss an exam, you can come in and make up an exam within a week of the day it's given. You get full credit as if you were here on the day of the exam. What I mean by that is many of my exams have bonus questions in it. So you can take the exam late within a week and you get credit for the required section and for the bonus section. If you go into the second week, then the bonus section is off limits. You only get credit for the required section. If you go into the third week, forget it. By that time, we've moved so far on, it's a waste of your time. You have to pick it up on your own. Mistakes. Sometimes I make mistakes. Sometimes I make mistakes in actually asking the question on the exam. I've had students say, what does this mean? And I take a look at it and says, I don't know. What was I thinking when I put that in there? You know, so I'll either tell them what I think it should be and help them get the right answer, or I'll just throw it out. And then I grade the exams, and if you go home and you look at your exam later and you say, wait a minute, that one should be right. So you write on it like recheck or make a note of some kind and hand it back to me. I'll check it to see if I made a mistake. Great. Because I grade from a key, you know, maybe I made a mistake in the key. Because I don't stop to look at the question. I just say, there's the answer. Does it match the key? Okay, good, let's go on. So I can grade it fast. Because my goal is, and I think I can meet it because we only have 5 students. On the day of the exam, when you finish the exam, hand it to me, I'm going to start grading it right there. So I've been fairly successful in getting all the exams graded before you leave class. So you don't have to wait. Think, all right, you know, which questions did I miss? Am I going to go back and study those? No, you know when you leave class, which ones you missed, where you need to, what you need to work on. And plus it's out of my hair. Already graded, I don't think about it anymore. We just move on. But you can use pencil, any color ink except red. Red's my color. Everybody knows about exam etiquette, you know, be nice to your neighbors. Put your cell phones, iPods, tape players, whatever. No headphones. Just put everything away. All you need is pencil, pen. You can have scratch paper if you want. I try to put enough room on the test so you can scribble on it, do your calculations. But if you like scratch paper, that's fine. Pencil, paper, calculator. That's it. And I want a standalone calculator. I don't want a calculator app on your phone. Smartphones are too smart. Okay. Now I have an app on my phone, but I'm not taking an exam. Let's see. There's weather policy, library services, all that garbage. And then the appendices. I put screenshots in the appendices so it kind of give you some guidance of what you should see when you get into the homework. Okay, that's what that's for. Even one of the problems is what you should see. Like this one on page 11, if you get incorrect, it's going to pop up with a box that says, no, that's wrong, and here's some suggestions. There may even be, let's see it here. One student told me that sometimes they have links to the chapter, the electronic chapter, so just take you straight to the chapter. But that may not be the case for homework. It's just a sign of my newness to all this. Okay, and then at the last page is a syllabus agreement. All you have to do is print your name, sign your name, date it, to show that you received it. You're going to read it and understand it. If there's anything you don't understand about it, ask me. Call me up, text me, ask me in class, whatever. I don't want you to have trouble in this course just because you don't understand something. That's not acceptable. I want you to understand chemistry. So if you need help, don't be shy. Okay. All you have to do is track me down. That's the hard part. Actually, it's easier this semester than it usually is because I'm only teaching 20 hours. Sometimes I teach 20, 24 here is max, but I adjunct other places. So my hours have gone up to 20. But nobody wanted me this year. So I've got a lighter load than usual. Okay, so let's look at chemistry. Let's see, I need to put that down and that down. I'll do that up. And start the slideshow. Okay, this thing's working. Batteries. Yeah. So I have an extra pair of wires. Big battery. Little batteries. Yeah, AAA. I'll break in 4 times. There we go. That was the problem. All right. So, let's check these shirts. Introduction to chemistry. Everybody remember the Grumpy Cat? Yeah. Chemistry seems to go down better if you can have fun at it. That's probably true for any subject. But we want to have fun. Poor Grumpy, rest in peace. He just passed away. He's filthy rich. His owners were filthy rich. Okay, these are the 3 chapters we're going to cover this first exam. That's just an outline. Let's get down to the meat. I always wonder if I'm going to put effort into learning something. I want to know why. I'm like a 2-year-old. Why does this happen? I heard a psychologist talking about that. When a small child says why, they just want more information. They don't really understand what why means. It's just they're asking for more information. But in this case, I do want to know why chemistry is important. Well, one of the things about chemistry that's important is that we get new materials. There was a time in human history where everything we had when we built houses or construct cities or whatever, we built from natural materials. You know, we might chisel stones in the shapes we want, or we might cut down trees and lay them together in log cabins. But those materials were, natural. They were made by nature, and we just sort of modified them. Nowadays, particularly in the 20th century, we engineer materials like those chairs you're sitting on. Those are plastic. They started out as oil in the ground, and some smart organic chemist just figured out how to turn that into a polymer and shape it into a chair. Those new materials are there because of chemistry. And not just those materials, but the drugs that keep us safe from, once fatal diseases or debilitating diseases are due to chemistry, pharmaceuticals. Now, chemistry is a really broad subject, and it covers a lot of ground. It's like the octopus that consumed New York. Got lots of tentacles, and it goes everywhere. That's why one textbook I saw calls it the central science. And I was putting it mildly. I mean, it wants control of everything. So when we talk about pharmaceuticals, most pharmaceuticals, with a few exceptions, are made by chemical means, but by biochemical means. That is, we use microorganisms primarily, and the chemical abilities of those microorganisms to make pharmaceuticals. But chemistry helps us understand how they do that. Sometimes we only make the precursors using microorganisms, and then we use non-biotic methods to modify them to what we want. They just give us the starting materials. That's very common. Energy sources. Everybody's worried about, energy drives our economy. That's one of the reasons that our economy is humming along, is because energy now is more available. In other words, and the fact of the matter is, we now are net exporters of energy, particularly natural gas. And that's all due to, chemistry and engineering. Fracking has made so much more petroleum and natural gas available. We knew it was down there, we just couldn't get it, until fracking came along. Energy sources, that's carbon-based energy sources, but there are other energy sources that chemistry is involved in. The green chemistry sources, like photovoltaic cells, like those panels out there in the distance. Chemistry was required to make the materials that go into those panels. Okay, and just a side note, it costs more energy to make those things than they'll ever produce in their whole lifetime. Food supplies, that's a big one. Chemistry is responsible for not only producing food in the form primarily of fertilizers, but in seeing that your food supplies are safe after we produce them. Okay. Let's see. We'll have to give biology some credit here. The Green Revolution occurred back in the late 50s and 60s when geneticists were breeding crops that could withstand various extreme environmental conditions. One of them was storms, right? Initially, wheat would grow up like that. You know, it would produce its seed on the top, and then a big storm would come in, lay it down, and it rot. So the effort for geneticists at that time, plant geneticists, was to produce strains of wheat that were short stature. So they'd only grow up about this high. So if you go anywhere in this country where you can see wheat growing in the fields, I don't think we have much around here. It's only going to be about that high. So you can have 50, 60 mile an hour winds come through and it just does like that. But they still require fertilizer. And most soils won't produce at their maximum capability without some additional fertilizer. Nitrogen for sure. In West Virginia soils, phosphorus is a serious deficiency. Potassium is not much of a problem. But if you ever look at a fertilizer bag, you see 3 numbers on it, right? Like, for instance, if you go to your garden shop, you'll see 10, 10, 10. That's 10% nitrogen, 10% phosphorus, and 10% potassium. Those are the 3 biggies. So fertilizers. And we can do some help for the environment. For instance, remediating chemical spills requires a fairly detailed understanding of chemistry in order to remediate a site. If you can. Sometimes all you can do is scrape off the top layer of soil and go dump it in a cave somewhere. But chemistry is responsible for a lot of pollution, but it can also remediate it as well. I don't know if you can think of others. There are probably a host of other things. And then you can have chemistry just for fun. Fireworks. Okay. So there are 2 approaches that you probably need to make simultaneously. There are the large topics, you know, the general concepts that you really need to know in order to organize things in your mind. Because I mean, when you back up and think about the universe, chemistry or physics or anything for that matter, it just happens, right? You know, whether you believe it's started from nothing or whether there's a creator involved, it doesn't matter. Not for this topic discussion. But things just happen. They're going to happen their own way. And chemistry, science in general, has developed ways of investigating how that happens. And we have these constructs, which I call topics. And that helps us organize things in our mind. But you have to realize that as far as nature is involved, it just does its thing. It doesn't say, oh, I need to do it this way so humans can understand what I'm doing. No, it doesn't work that way. So we have these general topics that organize the subject of chemistry for us. And then you have the details. And, well, sometimes they say the devil is in the details. That's why I say work as many problems as you can, different types of problems, because that's really the only way to understand chemistry fully and get comfortable with it, is to work lots of problems within time constraints that you have. I know if your course load is really heavy, you're going to be limited, but do what you can. You'll enjoy it much better if you understand it better. And the best way to do that is to work lots of problems and get bored. Okay, so what is chemistry? Like I said, chemistry is a broad subject, so we have a broad definition. Substances in the universe undergo changes. They go from one substance to another, like the chair I talked about. You would probably agree that if you knew how it started as the black goo out of the ground, ends up as blue plastic that you sit on, they had to undergo some changes, right? So chemistry is the study of those changes, how those changes occur. And naturally, we need to make distinctions between whether the change is actually a structural change to this substance, or if it's just undergone a physical change. For instance, melting ice. You know it's still water. It was water as ice, and it's still water as a liquid, right? So that's just a physical change. But chemical change requires a fundamental structural change in the substance itself. So that's what chemistry tries to define. Now, if you talk to a physicist, they'll say, oh, chemistry is just applied physics. And in some respects, it is. In fact, there's a whole discipline of crossover between chemistry and physics called physical chemistry. You know, and if you talk to anybody that's ever taken physical chemistry, they just cringe and say, thank God I'm out of that. You know, it's rigorous. Right? It's the only C I ever made. No, the second C I ever made. First C wasn't my fault. But physical chemistry, yeah, it was. And then, of course, if you're a chemist, you say to a biologist, biology is just applied chemistry. So it depends on who you talk to. Okay. How do you solve problems in chemistry? This is a general outline. Everybody loves word problems. No. Because word problems are designed specifically to confuse. Right? They have lots of information, usually, that's unnecessary to the solution of the problem. So it's your job to pick out what you need. Best way to do that is ask yourself, what's the question? What is the problem asking? Unless you know the question, you'll never get the answer. And with word problems, you definitely need to know the question so that you can tease out the information that's required. Sometimes the question doesn't give you all the information you need. You have to go find it. You know, you might have to look it up in a table. You might need a constant value, or you might need a formula that's not given. So first thing you got to do is, what's it asking? What is the problem? All right. So now let's try to segue that into the scientific method. Scientific method is also an attempt to answer questions. And questions usually arise when you make an observation. You see something in nature that you don't understand. And like Isaac Newton saw an apple fall, right? That's what they say. I don't know if it really happened. He said, why did that apple fall? Not everybody would wonder, you know. They just say, where did it fall, and has it got a worm in it yet? But scientists generally ask these questions, and that you make an observation, and that prompts a question in your mind. What's happening here? Sometimes you're only able to say what has happened. Why may come later. So you propose a solution to the problem, or a fancy word for that is hypothesis. Saying, if this happens, then I should expect this to be the result. That's basically a hypothesis. You're creating a scenario in which if you start conditions here, then you expect these conditions. Sometimes that happens in words. Sometimes it happens in formulas. If you can put it in a formula, then you can say this equals that. And Isaac Newton is a good example. His second law of motion is F equals ma. That stands for force is equal to mass times its acceleration. So what is it saying? If you apply a certain force, then you can expect this acceleration if it weighs that much. So that's a hypothesis, and it has proven to be true. That requires testing. I'm sure Newton tested it thoroughly himself before he put his neck on the chopping block and published it. But his Principia introduced this and a number of other subjects to the world. And they've held up over time. Now, this only says what happens. It doesn't say why it happens. He never was able to deal with that one. But we formulate a hypothesis, and then once you have the hypothesis, you're able to devise an experiment to test, to see if your hypothesis works. So in this case, what would you do? Well, you have a mass of some size, and then you apply a known force to it, something you could standardize. And then you measure its acceleration. So if you do it over and over again, we call that replicate. If you do replicate tests, your experiment, pushing this mass with the same force, that same size mass, you always get that acceleration every time. Right? So your experiment confirms that this is true. Now, it's not always the case. Sometimes you devise a hypothesis and it falls apart, doesn't work. But that's not bad, right? In science, there's no bad and good. Bad and good is ethics. Science is just right or wrong. So if it's wrong, that tells you that I better try something different. Right? It's like Edison. Somebody asked him about his 99 failures to make a light bulb. He says, I didn't fail 99 times. I just found 99 ways that it didn't work. It only takes one way to work, and I found that one. My 100th way created the light bulb. So failed experiments are valuable for the information they provide. So we make an observation, we formulate a hypothesis about what's happening, and that leads to an experiment to test if our hypothesis is correct. Okay? Anybody in here had statistics? No? Okay. So I won't digress on that topic. Anybody going to take statistics? No? Okay. That's a double whammy. Shut my mouth. Okay. So this framework for learning about the universe we call the scientific method. Actually, the scientific method is a subset of what they now call critical thinking. The problem I have with critical thinking is the same problem I had with cell phones when they first came out. Heard them talk about the brick. It's about that cross section, about that big with an antenna on it. Things were monsters. But the critical thinking is used by everybody, but nobody ever defines it. Because I don't think they know what it is. But we do know what the scientific method is. It's a way, a framework for gaining information and organizing it. Okay? It's really just a plan of action. And the plan can change. That's the beauty of the scientific method. It can change to accommodate the question. Right? So in the purely quantitative sciences like physics, their methods will always end up with numbers. For the less quantitative sciences, such as biology, you might end up with a list of observations. You know, it's a little more out there. And then there's chemistry, which is kind of in between. Some things in chemistry you end up with quantitative values. Sometimes you end up with qualitative information. But the scientific method is that plan of action that allows you to synthesize those results and gain some insight into natural processes. Now, here's my beef. Get up on my soapbox. If you ever hear someone say settled science in the same sentence, you have my permission to stand right in front of them and call them a liar. Because there's no such thing as settled science. That's an oxymoron. You know what that means? Those two words don't go together. Right? There's nothing settled about science. Science is always changing. If you can't question the results of someone else's work, then there's no science. Right? So when I hear settled science, I think lawyers. You know, they like yes, no answers. That's how they win cases. So when you get up on the stand, if you're an expert witness, they're going to grill you to tell them what they want to hear and be definite about it, right? They don't want to hear probabilities. Because in any scientific investigation, there's always the possibility of error. And beyond that, once you express your opinion that these results that you got from an experiment justify and confirm your hypothesis, then when you publish that information, anybody else is welcome to take that and reproduce your experiment to see if it works. So, why am I on my soapbox? It's because of environmental science. You know, global climate change. Man caused it all. The evidence doesn't support that. The science is not settled. Those are just people that are saying, we disagree with you, we hate you, shut up, sit down. That's what they're saying to you. So, science is never settled. It's always a process of gaining more knowledge and organizing that knowledge so that we can understand the universe better. I'm down off my soapbox now. So, this is a little flow diagram that tries to help show you the difference between laws and theories. Right? So, a law is like Newton's laws of motion. And all they say is, this is what happens. If these are the starting conditions, here's where you end up. They don't say why, they just say, this is true, it happens that way every time. That's a law. A theory goes one step further. A theory tries to explain why that happens. Now, Newton couldn't do it. His explanation for, say, gravitation was action at a distance. You know, that doesn't explain anything. It wasn't until Einstein came along that we had a plausible theory that would explain why the planets go in circular motion around their suns. And we don't have time to explain it here, but it summed up in one word: relativity. So, what are we doing? Well, we talked about this earlier. You make an observation, you form a hypothesis as to what's happening, and then you perform an experiment. And the results of the experiment tell you whether you need to make more observations and continue, job security. Eventually, you get to the place where you may be able to form a law, like Newton did. You feel confident in your results, and this is how things work. But if you continue farther along and certain conditions arise, science is a very plodding, slow, incremental investigative process. Right? It takes decades and centuries to really understand what's going on in nature. Chemists, well, alchemists, of course, back in the Middle Ages, were dabbling with chemistry then. Some of them were trying to turn base metals into gold. But along the way, they discovered some things. But it wasn't until the middle 17th century that we started, this scientific method started to emerge. It didn't happen all at once. And the information that was gathered didn't happen at once either. But eventually, you get to the point where you can formulate laws, and hopefully, at some point, somebody proposes a theory. That is, why does this law work? And that usually involves the creation of a model. And models, it's like model airplanes, model ships. The model airplane is not really the airplane. It's just a representation of the airplane. So the model in a theory is just a representation of this system that you're investigating in nature. Okay? But the beauty of the model is, if you created your model well and with sufficient detail, you can change things about it. Like what would happen with this model airplane if I changed the wings from straight to swept? What if I changed that model, took the piston engine out of it and put a jet engine in it? What would happen? The theory allows you to do that, make those changes. The law doesn't. The law is fixed. It only works for these circumstances, and you can't change it. But theories with their models, you can change significantly. And that's good because then you're able to investigate, does this why explanation really justify my confidence? So once you have the theory and the model, you can make predictions, which are not part of this process. You can make predictions, and they leave out the formulation of new hypotheses, but you can take this and put it as a subset right in here. Okay. You can make those predictions, which require that you make observations, hypothesis, test the hypothesis, and move on from there. And then what happens if your theory fails? If your theory fails to explain or properly predict an outcome, you have three options. One, throw it out, start over. Okay, that's rather extreme. What happens most of the time is modify it. Modify it so that it predicts more accurately. The other possibility is restrict. You restrict the application of your theory to just this well-defined system, and anything outside that system, you just say, don't use it because it won't work. Okay? That's what we've done with, not just with theories, but with laws. That's what we've done with Newton. All of his laws taken together work in the universe if we're not too big or too small. If we're in the, observable stuff. Planet size is okay. But once you get to really big, like neutron stars or black holes, it just completely falls apart. Or if you get really small, down to the quantum level, like electrons and subatomic particles, Newton doesn't work there either. So then you need a new theory to deal with those things. And for the very, very large, we get Einstein with relativity. For the very, very small, we get quantum mechanics. Okay, so you need two different theories for those. Now, Einstein worked his whole life. Once he established himself, then he devoted himself to unifying theory of physics. You know, he wanted a theory that would bring everything together in one theory. He never succeeded, but he tried. Somebody asked him why he did that. He said, well, I can afford to do it now. I'm already established, you know. I've got plenty of money, got a good reputation. You know, I can fritter away my days working on this thing. If I were young, trying to establish myself, I wouldn't attempt that because the chances of success are almost zero. Right? So that's what he did when he was young. He was like in his early 20s, working at the patent office in Bern, Switzerland. And in his spare time, he did physics on relativity, photoelectric effect. That's the one he won a Nobel Prize for. But he established himself there on problems that would give him good results. And then after he got his reputation established, then he could spend his time doing such stuff. Okay, so we've got the difference between law and a theory, what to do if your theory goes wrong. And let's see. That's everything I've said so far. Okay, let's say we have this description. Say I'm holding a balloon, and I quickly inhale some of the gas. Right, you know where this one's going, right? And I sound like Alvin Chipmunk when I talk. The pitch of my voice goes way up. So I ask you to determine what gas was inside the balloon. Based on your observations, are you justified in concluding that the gas was helium? What's missing? Well, let's see. You made an observation, right, that my voice changed when I breathed the gas. Right? So you formulate a hypothesis. Okay, we hypothesized that the gas that I breathed was helium. Right? So what's missing? We never tested it, right? Right. So how would you test it? Well, you would tie up your instructor and force them to the ground, make them breathe different gases. Right? So, and the only one that worked was helium. So then with that testing, you could say, yeah, it was. By the way, you don't want to breathe too much of that. I mean, it works for a while, but what are you taking into your lungs? Helium. You're not taking in oxygen, right? So you can pass out at best. So we stated the problem. We made an observation. The hypothesis, this could be considered a hypothesis, but we didn't perform experiments. Okay, chemistry is like a foreign language. You probably already guessed that. And it has a vocabulary. Right? It has various words that mean specific things. But generally speaking, the alphabet of chemistry is right over here. Chemical symbols. They represent the elements. And by using those elements in various combinations, we can describe on paper what's happening in a chemical process. Using those symbols plus numbers. Don't leave the numbers out. So we have to learn the vocabulary. So eventually I'm going to have you learn maybe half of those symbols. I've got a handout that I'll give you next week, so you can get started on it. But I don't think you need to know it for the first exam. You don't have to know the symbols, but you know, when you're memorizing something new like that, the more time you have to do it, the better. So next week I'll give you a periodic table with the ones marked off that I want you to learn. And then for the next section, which is chapter 4 and 5, I have a couple of exercises that are extra credit. And that hopefully they'll help you learn this stuff too. So very often you have to memorize. Actually, memorization is an underrated mental process. Memorization really disciplines your mind. And you may not realize it at the time. It's a chore, you know. But memorization, I think at the physiological level, anybody here had A and P? Yeah, okay. At the physiological level, memorization reinforces neural pathways, right? It really strengthens them. And that type of mental activity, in addition to others, is what keeps me from going insane. Because once I retired from the U.S. Department of Agriculture doing research, you know, my mind was stimulated every day. But soon after I retired, I just felt my mind turning to mush. It was scary. So I went out and looked for work. And I found a job with New River. First, I was adjunct. I was just teaching courses that they wanted to. And then eventually they hired me full time. But these mental activities are necessary to keep your mind from turning. I mean, it's like a muscle. If you don't lose it, it'll atrophy. So memorization is good. It's a chore and it's time consuming, but it's good. And then if you work a lot of these problems, then you learn certain procedures that help you solve problems. And whenever it's appropriate, I'll give you helpful hints, processes, procedures that will simplify solutions of some of these problems. You just have to practice them. Everybody makes mistakes. In fact, mistakes are the pathway to learning. If you don't struggle with a problem, then 99 out of 100 people don't learn. There are a handful, 1 in 100 people that just instantly see something, remember it. I don't want to live that way. You know, the reason being that at some point in your life, that talent is going to fade because your brain gets older. And when that happens, it's going to have a severe psychological impact on you. That's what I think. That's my theory. Anyway, always ask questions. Be asking yourself questions. Ask the book questions. Ask me questions. And try to find answers to them. A lot of the answers will be wrong. You know? But like Edison, those wrong answers just told you, I don't need to go down that road again. Right? And chemistry will become more fun and easier to deal with if it's more familiar. That's why I want you to work lots of problems, as many as you can. You have time to work lots of problems, and familiarity produces comfort with chemistry. Now, you've got the homework, of course, those are graded exercises, but you also have access in Blackboard to another set of problems that you can work. Remind me. Oh, we're getting low on time. Let me see. Am I getting close to being over? Okay. Yeah, because you guys have the, I never look at them. I only look at them up here, so I don't know what's coming. Oh, that is the last one. Okay, so let me go to the Blackboard and show you where those things are. I call them review documents. And that used to be the only way that my students were introduced to the subject and were able to reinforce their knowledge, was through these review documents. So I know they're tested and they work. But I never graded them. I didn't have time to. So that's one of the reasons, that's another reason that I'm using this homework application through Cengage, is because they do the grading for me. So I can get that assessment from you without any extra effort. There's a little extra, but not much. Okay, so if we go to the class, and then start here, lessons and reviews. Okay, this is where you'll find the PowerPoints. So for exam 1, there you go. These are end of chapter problem solutions. You can use them if you want. Here are the review documents. Okay. So there's review document for Unit 1, which is chapters 1, 2, and 3. And it's a fillable form. So you put your answers in it. You can use it as an exam, a test. I'm not sure if you can save this one. You might have to print it before it disappears. But then you have, here's the review key. This gives you the answers. Okay. But down here, well, this one doesn't have it. I should have used a different example. Later on, let's go to exam 2. There's your extra credits. You can look at them now if you want. I'll hand out hard copies. So let's see. I even have practice tests in Blackboard. Review documents. Here we go. Exam 2. So there's your form. There's your key. And here, beginning with the second exam, I have worked problems. So I take all the problems, most of the problems in the review document, show you how to work them. So if you have any trouble, it's better if you try to work it yourself. And then if you're still stumped, go look at how I did it. Let's see. Here it is. And it's all handwritten. I try to write as legibly as possible. And there's an explanation for the correct answers. Okay. So that's useful too. If you have time, go get the review document and look at those. Let's see. There's lots of information in here. On polyatomic ions. Actually, I need to print out some of these in next time, Thursday. Oh, we got 10 more next time. Or is it 50? 950 or 940? 940. Okay, so I've been talking all this time. You got any questions? Anything? Just screaming to get out. Okay.
Now I'm interested in more topics that I know are like so far out of my reach yet, like you were mentioning quantum mechanics and relativity.
Yeah.
My brother's a science major, so he talks about this all the time, and I have no clue what he means.
Oh, yeah.
But because you're talking about, I'm thinking, ooh, how can I look into this? But I have nowhere to start, so hopefully this will be the place.
Yeah, could be. This I just mentioned those here just to put things in perspective.
Mm-hmm.
Yeah. I don't know quantum mechanics. Not well enough, to major in something like that. Relativity is a curiosity. I understand some things about it.
Yeah, keep not like I said, my brother just does the stuff for fun. He's one of those boring. So we'll ramble on and on, that's what he's talking about. But if this will give me the foundation,
Yeah.
it'll at least let me be able to understand more. Things
Okay.
like that. I mean,
Yeah.
in my free time, look for that kind of thing. That's what I like to do. Can I do this?
Oh, yeah, sure. So you can ask him a question that maybe you can stump.
Ooh, I'd love to.
Yeah.
It's been years since I've done that.
Okay, so let's stop this.